All right, so I broke this up into two sections, maybe 3 sections, I can't remember. But the first one is the disk method. Okay, the disk method is the main one that's on your AP test. The shell method is not on calc AB, it is on calc BC. But it's just another way to find the volume. So if you want to use the shell method, you can. It's no big deal. And then the very last one is kind of like a very strange, like you're using the areas. I don't know. You'll have to see those to explain them. All right, so the first one is what we call the disk method. So let's go back to geometry. How do we find, how do we find the volume of something like number 1? Area of the base times the height, right? So hopefully you guys remember that it was always V equals big B times H, so area of the base times the height. All right, the bases are always the two parallel sides. So the two parallel sides are circles. So it's going to be pi r squared H. So it's pi times 6 squared times 20. Yeah, so 36 pi times 20. So you could have 720 pi, or, guys, 2,261.947. So either answer. What are your units? Inches cubed. Okay, so then that brings us to number 2. These are always the ones that my geometry students had trouble with. I see that everything's shifted a little bit here, but all right. So the reason my geometry students always had trouble with these is because it's hard to tell what the bases are. Can you guys tell what the bases are? Yeah, it's the front and the back piece, right? They're always the two pieces that are the same, and they're parallel to each other. All right, so what I was saying is it looks like my drawing was shifted a little bit. That should really be here, right? Okay, so in the bottom of our pentagon, I gave you this. This is 54, and this is 8 feet. So it says it's a regular pentagon. So each side is 8 feet on the pentagon. All right, so if I want to find the area of the whole pentagon, how many of these green triangles do I have? 5, right. Victoria, can you close that door, please? All right, so we need to find the area of that triangle and then multiply by 5 to get the area of the base. Okay, so the area of the base is going to be 5 of those triangles. So they're going to be 1/2 base times height. So what are we missing? Yeah, we need to find the height. So how'd you guys, you say 12 is this one? Yeah, the 12 is, it's kind of confusing. It's not the height of the triangle, it's the height of the whole prism. Okay, so let's go ahead and find the height of the triangle. Okay. If the whole piece on the bottom is 8, that means it's 4 and 4. It's metric. So how do we find H? What did you say? Not Pythagorean theorem, because we don't have 2 of the sides, right? Trig, right? So we're going to do opposite over adjacent. So we're going to do tangent of 54 degrees equals opposite is H over adjacent is 4. Okay, so make sure your mode is in degrees. Do tangent of 54, multiply by 4. You might want to store that as H or something, just in case you need it. All right, so I got like 5.5055 and so on. All right, so that's what's going in here. So my area of my base is 5 times 1/2 times 8 times that answer. So I got 110.11055 and so on. Okay, that's just the area of the base. So that's the area of one pentagon. Okay, to find the volume, you take the area of the base and you multiply by the height. So you're going to take that number and you're going to multiply by, we should be careful in calling it h, so let's call it h2 or something. Because it's a different height, right? So times 12. So I got 1321.327. You could have 326 or 327. Okay, the units on this are feet cubed, so cubic feet. Okay, does this make sense? Yeah. Those are always the hardest ones in geometry, finding the area of the regular shapes. All right, so when we don't have something that we know from geometry, so when we don't have cylinders or prisms, we can find the volume with a method similar to finding a Riemann sum. So if you guys remember when we found the area originally, we found all of the heights, and then we took an infinite sum, right? We added all of those heights together. We're going to do the same thing, so it's integration that we're using. Okay, so with area, remember we'd add up all the heights that we got, and we take an infinite sum. And what happened to the width of those rectangles? Remember, we let the width go to 0. Like we made them infinitely skinny. You know what I'm saying? So we used more and more rectangles. And we did this the long way. We did it with our sigma notation. And you guys hated that. Right? It's not on the AP test, so it's okay. But then we learned that that sigma notation was really the same as integration. Okay. So we're going to do the exact same thing with volume, but now we're going to add up all the different areas. So it's very similar to like cutting a piece of bread. So you guys see that picture where you're cutting it into lots of different pieces that have the same shape, basically, right? They might be getting a little bit bigger. They have the same shape, but we're going to add up all of those pieces to get the volume. Okay, so it says the same is true for a sphere. Let's sketch several vertical cross sections of the sphere below. So if I chop my sphere in half, what's the shape of the cross section? Do you guys know what I mean by cross section?
It's a circle.
It's a circle, right. So if you cut it in half, this is what's called a cross section. So it's like if you took an orange, you cut it in half, and then you showed the two pieces, it's the shape that's on the bottom. The shape along the cut. Okay, so do you guys see, it doesn't matter, we don't have to go in the middle, we could go right here too. These are all circular cross sections. Okay, so we could take an infinite number of these circular cross sections, add up the area of those circles, right, that have no width, quotes, no width, and then we would get the volume of that sphere. So that's what we do. Okay, this is called the disk method. So we call the slices disks. Once we find the volume, or not the volume, the area of each disk, we can add all of the areas together. Kind of, I don't know. You can think of it as volume of the disk if you think of it having a thickness, but we're going to have an infinite number. But what if there were an infinite number of, oh, I guess that is okay that I said volume then. So what if there were an infinite number of disks? Then we would not have individual volumes. Instead, you'd have areas. Does this make sense? So we're adding up the areas of all these circles. Okay, so the definition for volume for the disk method is this. So S is going to be some kind of solid that lies between like x values of a and b. So in our picture of the circle, maybe we only want to define from there to there. If the cross-sectional area is a of x, so it's always like a circle, and that area depends on where you're located. Like, it depends on what x value you're at, you know what I'm saying? Because the radius is changing. Do you guys see that? So it depends. It's still the same shape, but the radius might get bigger. Then the volume is this. Okay, so let's try. So number 1 says, find the volume of the solid obtained by rotating about the x-axis, the region under the curve, y equals the square root of x. Sketch a picture to help you. So we're going from 0 to 1. And a lot of times, well, always there is a free response question on area and volume. And in those free response questions, usually the first part is find the area from 0 to 1 under this curve, which we know how to do from the last section. Then part B is find the volume when you rotate it around the x-axis or the y-axis or something. Okay. And then sometimes there's like a part C that's using the third kind of volume that I kind of mentioned that we'll do later. Okay, so we're going to go around the x-axis. So think if you have that blue area and you rotate it around the x-axis. Can you guys visualize what's happening? What shape is created? It's what? Kind of like a hill, yeah, like a hill on its side, so you said? Yeah. So this is what happens. Those of you that aren't very good at drawing, it's okay. It's not reflecting, it's now spinning all the way around this very quickly. So when it spins all the way around, it creates a shape. Let me draw this a little better. Kind of like a bowl, but that bowl is completely filled in. Okay, so it's a bowl that has like concrete filled into it. Does this make sense? So you're creating a shape like that, and it's not hollow on the inside. It's all filled in. All right, so our volume is going to be integrating the area of each slice from 0 to 1. Okay, so think about what if I chopped a piece of this. So if I slit right through, like with a guillotine or something, you know, straight through. I know, scary. Yeah. So if I chop right through, can you guys see what shape's being created? It's a circle. Yeah, it's a circle. All right, and that circle has a certain radius. Okay, what is the radius of the circle? Ah, good job, Jenny. Do you guys see? It's just the square root of x. It depends on where x is located. If you were way on the end of it, if I was over here, my radius is 1. If I was at the beginning, my radius is 0. If I'm somewhere in the middle, my radius of my circle is the square root of x. So square root of x. Okay? So what's the area of the slice? So if the radius is square root of x, how do I find the area of the circle? It's what? Pi x, right? It's pi r squared. So it's pi x. Okay, that's what we're going to integrate. So I'm going to have from 0 to 1 of pi x dx. All right, the pi can go out front. You'd have a 1/2 x squared going from 0 to 1. So you get pi over 2, 1 squared minus 0 squared. So it's just pi over 2. Okay, so that's the area of that like bowl shape that's, or not the area, the volume of that bowl shape that's completely filled in. Okay, so let's try this one. So find the volume of the solid obtained by rotating about the x-axis, the region bounded by the lines y equals 2 minus 1/2 x. So if you write that in y equals mx plus b form, you see the slope is negative 1/2. The y-intercept is 2. You're going to go down 1, right 2. Down 1, right 2. All right, so we get that line. Y equals 0 is just the x-axis. X equals 1, and x equals 2. Okay, do you guys see our different lines? Okay, so this is creating this little area right here. So think about what happens when you rotate it. So you're rotating very quickly around the x-axis. a shape like that. Do you guys see it?
Can you erase that on the recording?
No. You're not the first one to be confused about the shapes. Trust me. All right. Okay, so again, we need to find the area of my radius. Or my area of my radius. I need to find my radius. My area of my cross section. Okay, so what's my radius? It's the 2 minus 1/2 x. Okay, so it starts out pretty easy. It's just the function. They will get a little harder. I know.
I don't get how you find the radius.
Okay, so the height, I'm basically asking for the height from your x-axis to any, for any cross-section that I choose. So the height right here depends on where your x is, and it would just be plugging into our equation of our line, which is just 2 minus 1/2 x. Do you see what I'm saying? You seem confused still. Okay, so if I was at 1, so if I was on my first one, if I was at 1, I would plug in 1 into my y equals. So you get 2 minus 1/2, so it would be 1.5 is the height. If I plugged in 2, so that's the next one, I'd have 2 minus 1/2 times 2, so that'd be 1 for my height. If I plug in anything between there, I just use x. So 2 minus 1/2 x. So x is changing. All right, so my volume is going to go from from 1 to 2, right? And it's going to be pi r squared. Okay, these are still circular cross sections. And when you're rotating around an axis or something, it's always a circular cross section. Okay, so we can pull the pi out front. We're going to FOIL. You could do a u substitution, but why make it hard on yourself? So I'm going to have pi on the outside. I'm going to integrate 4 minus 2x plus 1/4 x squared dx. Okay, so I have pi. I'm going to have 4x minus x squared minus, it's going to be x cubed, so I'm going to need a 1/12 out front. Right, 1/3 times 1/4. And I'm going from 1 to 2. Yes, plus, thank you. Who said that first? Oh. All right, so I get pi. When I plug in 2, I have 8 minus 4 plus 1/12 times 8. When I plug in 1, I get 4 minus 1 minus 1/12 plus 1/12. I keep wanting to make that a minus. Okay. So 8 minus 4. Okay, I got 19/12 pi. Is that what you guys got?
Yeah.
I usually leave pi in these answers because it's having to do with that circular cross section, so pi should be an answer. But if you guys write it as a decimal, that's fine. It's 4.974. Okay, remember 3 decimal places. All right, is this making sense?
Yeah.
Yeah? Not too bad? What's the number that's after what?
The 4 minus.
That's plus 1, or it's minus 1 plus 1/12. I have trouble putting the plus back in. My pen's off a little bit. All right, so determine the volume of the solid obtained by rotating the region bounded by y equals x squared minus 4x plus 5, so that's this one, between x equals 1 and x equals 4, and the x-axis around the x-axis. So this one I actually gave you a picture of, because it's kind of hard to draw. If you guys were drawing it, I mean, basically what I would do when I was drawing these is I'd create a circle, do a mirror image of that shape. Mine still doesn't look very good, but that last little line wasn't good. Okay, so that's kind of the shape you're getting. Okay, that's what's right here. Okay, it's all solid. Kind of like a table on its side. One of those little retro tables, maybe. Okay. So you can chop anywhere that you want. So if I chop right in here, that's x over, we don't know what x is. The height of that chop, so the height of the radius, is still just the function, x squared minus 4x plus 5. Does that make sense? No? Yes, okay. Thought I heard no. All right, so my volume is going to be pi r squared dx, and we're going from 1 to 4. This would take a little bit to multiply out. I will let you use Math 9. You are all capable of doing that by hand, but I would pull the pi out to the front, though, when you do Math 9. So that way you get your answer in terms of pi. Because they're acting like it's your birthday and I'm having a big party for you. Yes, Math 9. All right, so my setup looks like Math 9. So I hit Math 9. I get fin int. I put parentheses, x squared minus 4x plus 5 squared. X goes from 1 to 4. Did you guys do that? And then I took that answer and I multiplied by pi. So I got 78 over 5 pi, which is the same as 49.009. Don't just round that to 49. It's not 49, right? It had pi in the answer, so 49.009. Okay, so now let's do it around the y-axis. So find the volume of the solid obtained by rotating the region bounded by y equals x squared. From x equals 0 to 2. 2 down there. Ooh, this is an interesting region. So if you're going from y equals x squared and you're going below that, right, it's being trapped by that and the x-axis between 0 and 2. So we get that. I really should have said and the x-axis. So let's say region bounded by y equals x squared and the x-axis. I don't know if that's the region I want you guys to do. Okay, let's do the y-axis, yeah. So change this. I want to do an easier one for you before I get to the hard ones. So let's say and the y-axis. So let's do this piece. Okay, notice it'd really be over here too. No, 0 to 2, isn't it? Okay, so we're there. All right, so if I'm rotating around the y-axis, think about what shape's being created. A bowl filled in. All right, Now, think about the cross sections for this one. How do you get those circular cross sections? You slice horizontally, right? So must slice horizontally to get circular cross sections. Circular. And we like the circular cross sections because it's easy to find the area of a circle, which is pi r squared. We don't like chopping it vertically because then we have some strange shapes. Do you guys see that? They would be like little, something like that, like a weird shape. All right, so we're gonna slice horizontally. Okay, so previously when we were slicing vertically, here's what's happening. It's x is changing, and x is going from 1 to 4 in this last example. Okay, that's what this means. My x values are going from 1 to 4. Dx means you're changing your x values. Okay. So if I'm going to chop horizontally, what's changing? X values, y values? Y values. Yeah, so you're going from 0 to 4. You need to get it in terms of y. Okay, so need to integrate with respect to, WRT means with respect to y. Because the y values are what is changing as you change your cross sections. So imagine you're chopping, see how you're going, you're chopping horizontally, but your hand is moving vertically. Since your hand is moving vertically, that's the y values that are changing. So that should make you think, oh, y is what's changing. All right, so that means I'm going to have dy, and I'm going to go from 0 to 4, my y values. I still want pi r squared. What's my radius? Yeah, so we had y equals x squared before. If I want it in terms of y, remember that means we solve for x. We get x equals. So that would be square root of y equals x. And it's actually plus or minus, but the side we want is the plus, right? This is y, square root of y equals x. Okay, so we want square root of y in there. That makes it nice. All right, so you just have 0 to 4, pi's on the outside, you just have y dy. So it's 1/2 y squared with a pi out front, 0 to 4. Yep, so you get 8 pi. Okay, so just like with area, sometimes you have to integrate with respect to y. Next step. Okay, so what if I had the region bounded by y equals x squared, y equals 4, and x equals 0. So y equals x squared, y equals 4, and x equals 0. Okay, so x equals 0. Oh wait, x equals 0. Y equals 4, y equals x squared. We wanted to integrate with respect to x. Okay, so we're taking this piece. Okay, and you're integrating with respect to x. They didn't really draw this picture quite right. Okay, so if you're rotating around the x-axis, what happens? You get kind of the mirror image here, and then this creates the rotation. This is why I tried to get a picture, because it's hard to visualize. Since we're stopped by x equals 0, this picture should actually be just this piece, so just this side. Do you guys see what's happening here? what's happening?
Like gut.
Yeah. Yep, it's like gutted out, right? You scrape some stuff out. Some of you that take pottery would be very good at this because you're like scraping out the inside of your pot, right? That's what we're doing here. So it was like a solid piece, and then we scraped out this curved piece on the inside. Okay. This is what we call the washer method. Okay, so it's similar to the disc method. You're still using discs, but then you're subtracting out an inner disc. Do you guys know much about tools? Do you guys know what a washer is? Yeah. So washers are a little hardware that has a circle in between it. It's flat. I don't think I probably knew what a washer was in high school. I'm not very handy. All right. You guys don't know what it is? How many of you do not know what a washer is? Maybe we should bring a washer in. All right, so what's happening is you have the disc method. So the disc method's on the outer piece. You have the disc method on the inner piece. You're subtracting the two pieces. Yes. Yeah, so you're subtracting the volume of this piece right here. So Rachel said, now when you're subtracting out the inner piece, doesn't the radius get smaller? Yes. So you're going to find the volume of the cylinder. This is a terrible cylinder. So find the volume of the cylinder, and you're going to subtract out that inner piece, which is kind of like a funnel. So find this one first, and then find this one, and subtract them. Okay, so this is using something that we call washers. Okay, if you still call it the disc method, it's fine. I always still call it the disc method. All right, so number one. So the region R enclosed by the curves y equals x and y equals x squared is rotated about the x-axis. So we have this piece right here, and it's going to be rotated around x. Okay, so we have an outer shape, and we're funneling out an inner shape. So it's got kind of a thickness on the inside. The radius is very small. Okay, so what we do is we call the big radius capital R. So that stands for outer radius. The little radius. So do you guys see what I just drew? It's kind of hard to draw. Okay. So I drew the outer one, so from the x-axis up to that top point, and then I drew the inner one. Still can't see it, can ya? So here's the x-axis. I drew my outer radius here. My inner radius is here. Oh, that's little r. So capital R, little r. So outer radius, inner radius. Okay, so we're going to put it all together. So what we would be doing is pi r squared minus pi r squared, like that. So the way we end up integrating is we just pull the pi out front. We do outer radius squared minus inner radius squared dx. Think about your cross section. So as you're chopping, how's your hand moving? Horizontally, right? So it's vertical chops, but you're moving from left to right. So your x values are what's changing. So we're going from x equals 0 to, what's this intersection point? 1, 1. Because you'd set x equal to x squared, get everything on one side, pull out the common factor, you get x equals 0 and x equals 1 are the places where they intersect. So from 0 to 1. So I have pi from 0 to 1. Outer radius squared, what's the outer radius squared? So what's capital R, I guess, is what I'm asking. x. And what's inner radius? X squared. So you're going to have x squared minus x squared squared dx. Still making sense? Okay, it's just the two functions. The outer one was the y equals x. The inner one was the x squared. All right, so I have pi x squared minus x to the fourth dx, 0 to 1. So pi is on the outside. X cubed over 3 minus x to the fifth over 5, going from 0 to 1. I always like when it goes from 0 to 1. Isn't that nice? So 1/3 minus 1/5. So if you get common denominators, that's 5 over 15 minus 3 over 15. So 2 over 15 pi. That's your answer. All right, I'll stop there for now.